good morning, everybody. Thank you, Clara. Thank you very much for inviting me, presenting my research subject, and so I will present you mainly what we did with the Planck mission, observing the cosmic microwave background. And then we have, of course, discussion about this, and I can answer your questions and explain some details on particular points. And just after, I asked the permission to show you my 5 minutes contribution to what I think, where we are now with the space technologies. So, here is a kind of artistic view of the main results obtained with the Planck mission. This is the image of the microwave background on the sky of Toulouse, but this is a true scientific image from the Planck mission with about the right scale. If you could see it with your own eyes, if your eyes could detect the infrared and microwave light from the sky. And after the decontamination, I will explain you decontamination of all the astrophysical lights on the sky. The final image, the relic from the Big Bang, the image, that's almost directly an image of what happened in the very beginning of the Big Bang, the period that scientists call the inflation, when everything is supposed to happen from almost nothing. And it's a very weird theory. I will not be able to explain you the detail of this because it's theoretical physics. It's not really very much constrained today, except with this kind of observation. And I will explain you why this image that's very far on the sky is an image of the microscopic baby universe when it was created. And so the title of my talk is Space Astrophysics, a window on the origin of our universe. So to explain why we go to space with satellites like Planck, and there are many others in the end, I will show you the agenda of our science space missions for the years to come. So it's basically a question of the atmosphere is really a problem. And you have at the top of this slide the atmospheric opacity. So when it's 1, it's bad, and when it's 0, it's good. And so from the very short wavelengths, so the scale, the horizontal scale is the wavelengths in a fraction of a meter. So 1 meter is here, and you go to micrometer, nanometer, and on the left side, on the right side, you go to 100 meter, kilometers. So visible light, of course, is here with the blue to red colors. It's a very small portion of the infrared sky, and of course its atmosphere is transparent here. But then whenever you are at high energy X-ray, gamma rays, or far infrared energies, so I will use the term far infrared microwave for the same kind of radiation. It's a wide range, it's the range where the Planck mission has been able to observe. It's right in the middle here. The sky is transparent again to the radio wavelength, so that's why we have large radio arrays on the ground. And it gets, light is blocked again in the very long wavelength range because of the ionosphere. Maybe you know this physical mechanism. So there is a problem with the opacity, and not only the opacity, the atmosphere is really a problem because it is distorting the light coming from the space, and this light from space is very tiny. You know that we want to observe very far objects, and so the light is tiny and difficult to observe And all the light that the atmosphere will emit, the light from the Earth, the natural light from the Earth, are our problem. So, to go a bit further, this is, if you, tonight, if the night is clear, maybe not tonight, but this week, if you happen to have a clear sky above your head, so you will be able to see the Orion constellation that you recognize here. It's a beautiful constellation, and if you are very careful, okay, so I recommend you to have a look to this very, very nice constellation on the dark sky, because there are new stars born there, and they are all born from this tiny nebula in the middle. And sorry, I don't have the laser here. Maybe I can try this. Yes. So here is the Orion Nebula. And then when you go to the infrared, here is what you can sketch up. It's emission everywhere. So this is not really the infrared, sorry for the experts. This is the radio emission from the CO molecule, but the infrared from dust is almost the same. So those are fake colors just showing where is light. So red is a lot of light and blue is more light. And so what you see here is that in the dark you have emission from gas of hydrogen, helium molecules, and dust everywhere. And this is what makes the star to be formed, the stars with their planets. And also, the more distant you go, you will see assemblies of stars, dust, gas that are galaxies, ensembles of galaxies. And you have this everywhere on the line of sight, and this 90-degree turn is how this is deploying on the line of sight. So, come back. So this is the sky, and all the light is coming to us and is forming this single picture. But it is a superposition of many lights coming from many different objects. So this basic sketch is not at all with the right scales, so we have to simplify. So we are here with our Planck satellite observing the sky, and so the basic principles are that the further are the objects, so this is a scale of distance in light years. So our galaxy, which is full of gas, dust, stars, what you could look on the previous image, is as large as 100,000 light years. Then when you go to billion of light years, you see different galaxies. The galaxies are those small white dots here, and sometimes the galaxies assemble, group together. This is a cluster of galaxies. It's also really interesting. And so if you could go to the furthest, then you cannot go further than the Big Bang. So why is it so? Because you all know that light needs a certain time to travel. This means that when you get the light from 100,000 light years, this happened 100,000 years ago. So when you go to distant galaxies, 10 billion light years distance, this means those galaxies existed 10 billion years ago. So the Big Bang we think happened 13 billion and something years ago. So this means that if we could have an observation to this distance, then we could see the Big Bang. Unfortunately, we cannot look at the Big Bang directly because there is a kind of screen, and this is a screen I was showing you on over the sky of Toulouse. We succeeded observing this screen here that we call the last scattering surface, just that you have an idea of what happened. So First, we think we have the Big Bang. Big Bang is just the universe is coming from nothing, and very high energy density, very small, and it's expanding at very, very high expansion rate. Then it's cooling down, and this pure energy, we don't know exactly what it was, but after a few seconds or fraction of seconds, it gets transformed into normal matter, basically the matter we live in now. And with also, you know, dark matter or dark energy, but we don't know much about those dark energy and dark matter. And so this is the zero time here from the Big Bang. This is the other scale on this view graph. And 300,000 years after the Big Bang, the universe got cool enough so that this hot gas that was basically a plasma, this plasma on the right transforms to neutral matter, so normal, standard matter that we live with. And you know, plasma is always an opaque medium to radiation. Actually, to high temperatures, it's a luminous, opaque kind of cloud. So that's what I was trying to sketch up on the right. And then when it transforms to neutral matter because it's cool below a few thousands of degree Kelvins, then it gets transparent and the light can travel in all directions. And this is why we have this appearance of a last scattering surface that at the time it was created, it was a kind of a white, visible light. But with this phenomenon of the expansion of the universe, when we observe it now, we observe it much cooler in the radio range, and the apparent temperature of this maybe 3,000 degrees gas, we observe it at 3 degrees only, 3 degrees above absolute zero. So that's almost absolute zero in terms of temperatures. So here is the Planck satellite when it was under integration and system tests at Thales Alenia Space in, I think this was in Mandelieu and Naples, because they were the prime contractor for this satellite that was contracted by the European Space Agency. So it's a big instrument. And for a big instrument, of course, you need many countries, many scientists to work together, and those are the logo of all the institutes that contributed to this construction, with ESA managing it. And here in Toulouse, we are with IRAP. So the Planck satellite has gone to a L2 orbit. To be very short, an L2 orbit around Earth is an orbit that will have a duration of 1 year. And if you make it in the right clock direction, with the Earth going in 1 year around the Sun, then you try to visualize it, then the satellite will not move with respect to the Sun and the Earth. It will just follow the Earth 1,500,000 kilometers away from the Earth around the Sun in 1 year. So why we went there? Basically because we wanted to be far from the Earth. That's a big worry, emitting a lot of infrared and microwave emission. And we wanted to detect very low levels of microwave and infrared emission. So we wanted to go far enough, but not too far, because we need to communicate each day with the satellite to get our data back. So this position is very convenient because it is almost stable. So the launch happened on the 40th of May 2009, and my video does not go, sorry. Okay, so where is the full screen presentation? Is here? No. Here. Okay. So, here is the result. So with the Planck satellite, we were able to get those 9 full sky images of the radio and infrared light. The different images are different frequencies, different wavelengths. So this is the far infrared, and on the top left is the radio. And of course they are all different. They are all different because all those galaxies, gas, dust, on the line of sight, they have different temperatures. So this is a very physical, basic physical principle. Each object is radiating light with what we call the black body law of emission. And different temperatures in the object imply different black body laws, and so this means emitting at different frequencies. Here, at the highest frequency, you get all the dust and gas from our galaxy. So this is basically our Milky Way that develops throughout the sky. Then when you go to the radio, this is kind of diminishing. And in the middle here, on the upper and the lower parts, there you get the very, very distant last scattering surface, almost to the Big Bang. Just remember, just only 300,000 years after the Big Bang. What you have also are all the lights from the galaxies. So our galaxy, the galaxies down to the last scattering surface. And so as the different emissions look different in the different image, you can easily imagine that with a simple mathematical treatment, we will separate the different sources of emission. And then I had also a video to show this, but I will stick to those images. And just to be clear about what are those red and blue colors, it's only coding the intensities that are proportional to temperatures, coding in different colors. So this is a comparison with what you do when you observe the Earth with an infrared imager, the upper part of my slide. And so you code the temperatures of the oceans from 5 to 25 degrees, the temperature of the continents from minus 55, to plus 35 degrees Celsius. And so you can, of course, understand what happened on the Earth. That's warm on the equator, cold on the South Pole. There are the problem with the clouds also that are blocking the light. And here we come to the image of the sky, full sky. And this is the code of the colors in degrees Celsius, just for fun, because we never use those kind of units, but just to have a direct comparison. So this is the darker, the cool, very cool points are minus 270, 4252 degrees Celsius. And the very warm red are minus 270.4248. So these are very small differences in intensity and temperature. But and also you have the problem with the clouds. Here the cloud is the Milky Way in the middle. So it's not really opaque. You can recover the light behind this, but it's more light. And so more light is always more noise. And but everywhere else, you are here with the light from the Big Bang. And sorry for this, it will not work. Here is the result, part of the result. This one is the intensity of the emission of the cosmic microwave background all over the sky. And maybe it is difficult to understand, but from this image that looks noisy, actually this is not at all noisy. This is the last scattering surface, this gas that came from the Big Bang with small difference of temperature from one point to another point. This means differences in pressure. And there is a lot of information in this. And I will not detail how we do this, but from this image, we are able to derive almost all the cosmological parameters with a precision better than 1%. And this had never been done before. So we get, of course, the Hubble constant, but we get much more. One thing that we got here, that was one of the big questions, is how many species of neutrinos we have in our universe. You know, the neutrino are some kind of web particles that do not interact very much with matter, but they happen to be a lot of neutrinos from nuclear reactions. And our sun is emitting a lot of neutrinos. And there are 3 different species of neutrinos, but there was a question there could be more number of neutrinos. And Planck was the first to give the answer. There are only 3 neutrinos, so it's for the physicians. So I come back to my deep sky, just to be very clear. So this is a perpendicular view from this view. This image is all over the sky, up and below, because well, we are at the dimension L2 point, there is no more Earth, so you can have this image everywhere. So this is how this develops, and the image comes from this last scattering surface. So we did not just got the intensity, the temperature of the cosmic microwave background. We got its polarized intensity. To be simple, light is just what happened between 2 electrical charges. You move, you agitate one charge here, and at a distance another charge will move because this charge is moving. So the information went there with energy, and this is what is light. Okay? So if my charge moves in a regular way like this, it will emit a polarized light, a linearly polarized light in this direction. Okay? So now when we look at this, we have a direction of the sky, and that's the direction, the information that we are able to plot on the sky. Maybe it will be in the next, no, it's not on this one. Think to my very first image. There were red and blue colors, but there were also some lines. So those lines were figuring the direction of the polarization of the light from the sky. So now we go to things that I will not try to explain with my hands. But maybe you've heard of this controversy that happened in 2014, 2015, because when you go and you are able to detect this polarized emission from the cosmic microwave background, then there is one thing that the scientist is interested in, is there in this polarized map a sign that from the Big Bang gravitational waves were generated. Not the gravitational waves like those that come from merging to black holes that you've heard from. That is very impressive, not those ones. But the Big Bang in itself is something considerable. And with some theories of the Big Bang, they are predicting gravitational waves everywhere. And so those gravitational waves, they will distort the image of the polarized emission of the sky. And that's what the cosmologist observer are trying to detect. And there was quite an announcement that was famous in 2014 from the international team of the BICEP2 experiment at South Pole. That's one of the telescopes that you have a photograph here on the South Pole, American base. And they have instruments similar to the Planck mission, with that are more focused on particular on this science objective and detecting primordial gravitational waves. And they announced a detection beginning of 2014. And we were, all the Planck scientists, trying to look if there was that kind of emission in our data, and we found nothing. In the end, working with those guys to compare our data. And so this is what they got. A small patch of sky, colors for the intensity, and small black tick for the direction of the polarized density. This is a well mathematical operation. We are able to decompose fields of vectors in E-mode, B-mode fields. Well, this one shows you can see they are different in the nature of how the black marks are oriented. On this image, you have kind of spiral features that you have not on the upper one. In mathematics, that where you have rotational and where you have only divergence. Sorry, but so that's mathematical notation. So the primordial gravitational wave come in the B-mode here, and so that was the claim of the detection. And this is a full sky that we released in January 2015. So 1 year after the claim they got B-modes on the Antarctica data. And this is our full sky of the polarized emission in the wavelength range where the dust is dominating. So here you cannot see the emission from the last scattering surface. You have basically, this was also a great discovery that Planck made. All those features, what you see here with those lines showing the polarization of the this is dust emission from dust in the galaxy. And those lines that are built from the polarization of the light emitted by dust, they just show you that dust is aligned with the galactic magnetic field. And this alignment, for instance, is very evident here because you have, those are the line of the galactic magnetic fields that you see here. And so in the bottom here is the region where the BICEP2 team, where they did the measurements. And of course it is a region which is cleaner with respect to this very strong dust emission. But it's not all clean. And actually, now we agree. What they detected, what they announced to be the B-modes from the last scattering surface is actually dust emission from dust in our galaxy that's aligned with the magnetic field. And we were able with Planck to come to this conclusion because we had our different frequencies, our different wavelengths. And the BICEP2 guys, they had only one frequency for their measurement. So this is yet to be looked for, because there is no B-modes, no gravitational waves to a certain detection level. And you can always imagine that you would be able to go to lower level of emissions and you could get this information. So this is this beautiful full sky image of the polarized cosmological light, where if you are a mathematician, it's obvious there are only E-modes in there. It's a question of symmetry of the pattern. And I'm coming to the end of my talk, and then we can have a discussion on this subject. But before I finish, I want to show you the European agenda of space and ground-based astronomy for the years to come. So what is decided as an astronomy tool to be constructed and to be in operation in the decades to come. So next to come, you know, it is a James Webb Space Telescope. It's been a very long period of construction. It was supposed to cost only $1 billion. Now it has cost 10 billions. And it's a 6-7 meter telescope that will be refrigerated, able to do observation visible and the infrared in this wavelength range in the middle. And so that would be a fantastic tool that will replace the Hubble Space Telescope that's only 2.5 meter diameter. So it's coming to be launched in 2018, if everything is correct. And Europe, of course, is participated to the JWST, which is also led by NASA, as you may know. Pure European astronomy programs decided and to come soon are Euclid, and they are positioned here on my wavelength scale. So Euclid, coming in 2020, is a visible infrared telescope that's dedicated to understand what is dark energy. So if you have questions, we can come back to this. But in Europe, we decided to construct a satellite with a telescope and instrument that will be dedicated to this problem. Then in 2024, we have the Plateau satellite. You see Plateau, maybe you can guess it. It's 20 or 30 small telescopes looking in different directions to the sky, and it will track the eclipse of exoplanets in front of the stars that are the bright stars in the sky. And because we know now a lot of exoplanets because they are occulting their star, but for faint stars. And then with the large telescope on Earth, we are not really able to go further to analyze how those exoplanets they are, in particular if they are in the habitable zone. And so there are many questions about these exoplanets. And so Plateau will let us know all the exoplanets around the bright stars. And then we can use our telescope at the ground to go further and maybe to have someday an image of those planets, to know if they are like Earth or if they are very different. I'm going to the ground now because it's also some very great astronomy there. And we have 3 big projects of observatory to cover the different wavelengths. There is the big European extremely large telescope, kind of 40-meter diameter telescope, that's starting building now to be in operation in 2024 for the visible range. For the high energy range, we have decided, and France has just decided to go on the construction of the Cherenkov telescope array. It's where the range bands of big telescopes that will be set in Chile or in the Canary Island, maybe the two, and to perform analysis of the very high energy light coming from the sky. And on the radio side, you will have, by the end of the 20s, the square kilometer array, probably in Australia or in South Africa. And for space astronomy, Athena is a big and performant X-ray telescope that will be built by Europe, and it will be launched in 2028. And last but not least, something very different is also coming. All that I showed before were observatories that are able to detect the light. And ELISA, that is supposed to be built in 2034, will be an observatory of the gravitational waves. So this artistic view shows that with 3 satellites in the solar system that are in fixed position with respect to each other, and interfering with laser, very precise methodology, we will do the detection of the gravitational waves coming from the black holes that are going to, that are in binary assembly, turning around each other and going to merge someday. So this is, and probably many other objects that we have not seen to right now. And this is the end of my talk. Thank you very much. I'm not myself able to answer this, but I can try to do something. Neutrinos, they are like the light, they are relativistic particles. And so there is something very, so they are like a gas of relativistic particles, moving in all directions. And if they are a lot in number, at the period of this recombination, 300,000 years after the Big Bang, remember it was a hot plasma, 3,000 degrees. So everything was thermodynamically in equilibrium. So they are mixed with gas of non-relativistic particles. There is another gas of relativistic particles, that's the light, the photons. So there is one type of photon, a certain number of types of neutrinos, and all is thermodynamics. So if you study thermodynamics, you remember that the number of different particles is always something very important in the expression of the entropy or the pressure of the different gas. And all this is equilibrating. So now I come back to the image, but basically this universe is in expansion, and a gas of relativistic particle has a very different expansion equation of state from what a gas of non-relativistic particles has. So if there are many types of relativistic particles at this period, then at a very small scale, something different would happen. So that's something statistical that happens at the small scales, because how the pressure is related to the temperature when the gas is expanded is not the same for a gas of relativistic particles and a gas of normal particles. So I'm sorry, I cannot go further into the details, but basically this physical difference that implies a difference in this image of the small scales.
It's more of a general question. How do you determine the age of the radiation you observe in space?
Well, we're not able to do this. It's there is something very simple that generally the astrophysicists do. That's what we call the redshift. So the light from a star, it has lines, black lines or absorption lines that are positioned at a peculiar frequency, or emission lines. For instance, the orange light from the public lighting is the doublet of sodium, you know, it's not a white light. So the same from the stars. You have that kind of doublet, you have the same kind of emission from hydrogen gas, so there are many different in addition to the continuous light. So, and then so it's emitted from an object that's very far away from us, and because there is the expansion, we can relate the frequency shift, the Doppler shift, to the distance of the object. But you would ask me, well, also go ahead.
Yeah, but does it apply to the cosmic background?
Yes. And that's why I started telling you that that light, when it was emitting, was a white, the same as if you have a plasma lamp here, the light of the recombination surface that was 3000 degrees was yellow-white, you see? And now it's radio. So it's a factor of 1000 shifts in the frequency. You see that the frequency has been divided by a factor of 1000. So it's gone from the visible to the almost radio. But as this is white light, this is not a way to measure the redshift. Sorry.
How do you filter out the stellar component of the radiation? Is it with black body extrapolation?
Well, stellar light. So there were not. First, there were no stars at that period. Maybe they were. It's interesting, but we assume there were not. Basically, there are several ways to answer. First, even for our galaxy, that's very close to us with no redshift, the light of star shines basically in the visible, the near infrared. So they do not shine very much in this wavelength range. We could detect some stars, but those are the very, very bright stars with dusty envelopes around emitting in the infrared. Yeah, I was working on this subject with some colleagues. It's really fascinating, but there are very little of that sort. And also, this instrument has a very low angular resolution. Basically, the angular resolution of Planck is the same as the angular resolution of your eye. So it means that the stars, they are diluted, and so the light from the stars in our galaxy, we almost did not detect it. Just basically it's faint in this wavelength range, and it's diluted. I don't know if it answers.
I will frame to those observations with Planck determine the location of the Big Bang relating to opposition in the universe?
It's an interesting question. So you have to forget all this. The Big Bang is not somewhere. So the universe was not a big dark, and the light has come on a singular position. No, that's not how is the theory, and how it is consistent with the observation. And there was not an empty space before that Big Bang came. You have to change your mind. So it's it's an everywhere, very hot that came from nothing, not even a vacuum. So you have to forget that there was a vacuum before the Big Bang, because so here we come to some philosophical thoughts. If you have a perception of distance, it's just because something happened. Time and distance exist only when you have energy and matter changing, moving, and the Big Bang is the further we can go back to think with our physical principles of what happened to the universe. So it was everywhere, on very tiny distances, and basically the volume of the perceptive universe was very small at that time, but it does not mean that there was something outside. Everything is inside. Something that's also difficult to think to, but it's clear since 100 years now, is that our three-dimension universe can be closed at very long distances. It's just geometry with general relativity, and it does not mean there is a fourth dimension. It's not even that time is the fourth dimension. It's just that if the metric is not straight like Euclid, and it means if in a triangle the sum of the three internal angles is not the well-known fixed number, then we can have closed universes. And before being closed, universe can just be with some curvature and be open. With this theory of inflation, where physicians think about what happened in the very, very beginning. Very, very beginning is 10 to the minus 40 seconds. So is that those are only considering states of energies. There is no matter like that matter here, no atoms, no quarks even. It's much before higher energies, and data is very high energy together with, would say, very basic principle of general relativity. You have a very, very quick expansion. Actually, you can think to it this way. You know the dark energy. The dark energy in the universe now is something that's fixed in a fixed volume of universe. Well, at the period of the very beginning, there was something similar to this dark energy that we call inflaton, because it ran the inflation. It was not a dark energy, but it was similar in behavior. It was a kind of dark component of energy, very, very dense. And this term, when it's put into the cosmological equation of Einstein, that's not trivial to know, but it leads to an increase of the expansion rate of the universe. So actually we discovered the dark energy just because we observed that the universe actually is accelerating its expansion rate right now. So, go back to the Big Bang, in this very, very beginning. So the physicians, they think there was this kind of very, very high dark energy, which is inflaton, and which is a constant energy per cubic volume of universe. So it leads to exponential expansion of the universe. So the universe is that big. So it gets bigger. So it's bigger, it's more volume. But the energy is always the same. So it's more energy. And more energy, then it means more expansion. So more volume. So the first idea was paradoxal. When the physician came with this idea, they call it eternity inflation. They had no way to stop the inflation. And so one of the problems was, how do we stop this? So since then, of course, they found a way to stop it and to fit the reality. And so that's very strange, but those are theories, and in hand what you have is only what you know about general relativity that drives how the content of the universe is in mass and energy, makes it geometry, and we have a few principles of the physics of particles. You see, the particles are things that derive from fields, and that's very few, and we have almost no observations. And so that's one of the theories that have many, many developments, and actually the Planck measurements was able to limit the different theories, but there are yet many different ways to do this.
So maybe a last question? Okay, no last question. Thank you very much.
Thank you.